Hi, this is a supplemental video for Chem S-17 about the topic of aromaticity. This is one that I decided to not cover in section just because it's typically a more straightforward topic, and I think some of the other topics from this lecture deserve a little bit more time. So let's jump into it and talk about what is aromaticity. Aromaticity is this chemical phenomenon that happens where conjugated rings are unusually stable, like very, very stable. And they're more stable than would be expected of the same amount of conjugation that's not in a ring. So like if we compare benzene here, which is a ring and it's conjugated, to this hexatriene, where it's just this kind of straight chain molecule that is not fully connected here. Like the only difference is here in benzene, you have a single bond kind of closing it and making it into a ring, whereas the other one is not a ring. That has a huge difference in energy. The difference in energy is 36 kcals per mole. And I know that like most students do not have a good idea of what that means or like the significance of that, but when you do ATP hydrolysis to like fuel reactions in a cell, that's about 7.3 kilocalories per mole. And so truly having this extra bond here, making this a ring, yields like 5 ATPs worth of energy, just to give kind of a biological scale of where it's at. So let's talk about like why it is more stable as a ring. So each of the atoms in the ring has a p orbital because, as we know, conjugation only happens when electrons are delocalized in p orbitals. And they have the p orbital lobes above and below the ring. And essentially the electrons can spread out in a circle above and below the ring in these two kind of lobes, the above and the below. And electrons just really like that. Like the way I tend to think of it is it's kind of like the electrons get on a little electron hamster wheel and go around and around and around and around, and they're like, wow, I'm so stable and happy. Yay, such happy, so stabilize. But that's the essential kind of gist of aromaticity. It's rings that are conjugated are very stable. And we have this 4-pronged test for something to be considered aromatic. So the molecule has to be cyclic. So again, that's kind of like the difference between this and this, whereas this is not cyclic, so it can't be aromatic. It has to have continuous p orbitals. So a molecule like this one right here. Here, like you have p orbitals on these double bonds. And then you also have an empty p orbital here with a carbocation, but this atom is sp3 hybridized. There's no p orbital. So this lacks conjugation at a spot. So it doesn't have that continuous p orbitals. The third requirement is the molecule has to be flat. So if something is kind of bent like this, it is not going to be aromatic. Generally for our class and for most examples you will see, you can assume that molecules that appear to be flat are flat. We won't ask you to like predict when something's not going to be flat because that's kind of asking a lot. The last requirement is the weirdest one, and it's that there has to be a Hückel number of electrons, and specifically a Hückel number of pi electrons. So a Hückel number is a number that can be written as 4n plus 2, where n is a like whole number, a natural number. So like, for example, 2 equals 4 times 0 plus 2. 6 equals 4 times 1 plus 2. 10 equals 4 times 2 plus 2. In other words, like another way to think of it is you start at 2 and you just add 4 to get to the next one. And if there are these numbers of electrons, anyone in this list, that are delocalized in the ring, then you would have the last requirement for aromaticity. You would have a Hückel number of pi electrons. So like, for example, up here, you would have 2 pi electrons in this pi bond, 2 here, 2 here. That's 6 pi electrons. So that's a Huckel number of electrons. For something like here, which this is cyclobutadiene, this only has 4 pi electrons. So it fails this Huckel number condition because 4 is not one of the numbers here that is kind of special. The reason why this is important, I'm not going to go into. It's like a quantum mechanics thing, and it's just kind of complicated, but this is the thing to know. Another thing to kind of verify is like if we had something like this, here, these lone pair electrons would be in a p orbital, and so they count towards our pi electrons. So you would have 4 pi electrons here, a positive charge has 0 electrons. An empty p orbital has 0 electrons. So this would be the same thing, and in fact, this is just a resonance structure. But, okay, here so are 4 requirements, and then you are going to evaluate compounds and have to say whether or not they're aromatic. That's kind of the big thing. So if it satisfies all 4, it's aromatic. If it fails to satisfy 1, 2, or 3 here, if it's either not cyclic, doesn't have continuous p orbitals, or is not planar, then it's classified as non-aromatic. So that just means like she's not special, she's just normal. Non-aromatic, does not apply. But there's something really weird that happens. When you have these first 3 satisfied and you do not have a Huckel number of electrons, you kind of get like the evil supervillain version of aromaticity that's bad, and we call it anti-aromaticity. So I kind of think about aromaticity and anti-aromaticity kind of like bonds and anti-bonds, where like if you have this stabilizing thing, there also must be something that's destabilizing to balance it out, kind of just conceptually. And that's kind of a wishy-washy thing, but that's just how I kind of think about it. So anti-aromaticity is another chemical phenomenon where a conjugated ring has an unusually strong destabilization, where it's like even more unstable than the version that's straight chain. So compounds that are anti-aromatic are really, really unstable and just do not want to exist, and then they will do crazy things to not be anti-aromatic. So for example, this cyclooctatetraene, this is the example I showed earlier very briefly. Here, if this molecule was flat, which like sp2 hybridized, it wants to be flat for the most part, it would have 2, 4, 6, 8 pi electrons, and it would be cyclic, continuous p orbitals, and planar. And so it would be that situation where with 8 pi electrons, that's a non-Huckel number, and so this would be anti-aromatic. And so to avoid being anti-aromatic, this molecule doesn't assume its ideal geometry of like flat planar. It is going to pucker and bend intentionally so you can't have those p orbitals lining up. Like these orbitals are not going to be directly aligned with like these orbitals or these. And it's doing that so that it just fails this planar criterion and then is non-aromatic. And so this thing is like not particularly stable or unstable, but this version where it's flat is a very unstable. So it's going to do this crazy thing to avoid being unstable. So, yeah, that's essentially the gist of it. And that's kind of a rough introduction to it. So let's look at some examples from the homework, from the problem set, skill builders, to diagnose aromaticity. So I'm going to go in kind of a random order, just in terms of like doing the harder ones later, but it will seem like I'm doing a random order. So let's start off with this example. So we first do, is it cyclic? Yes. Second, we would do, are there continuous p orbitals? Well, our lone pairs are adjacent to a pi bond, and so by our neighbor rule, we know this is sp2 hybridized, and so the lone pair is in a p orbital, yes. Is it planar? Yeah, it looks to be planar. Do we have a Huckel number of electrons? Well, we have 2 in here, 2 in here, 2 in here, so we have 6 pi electrons. So if we list out our Hugel numbers, 2, 6, 10, 14, 6 is one of our Hugel numbers, we are good to go. So this thing is aromatic. Let's look at this one here. So first off, is it cyclic? Yeah, like I say, a ring. Second, do we have continuous p orbitals? And we have them here, 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 here. Ooh, this is sp3 hybridized. We don't have a p orbital, so fails. So if we fail one of the 1, 2, 3s, we would say it's non-aromatic. Okay, let's look at this one. Cyclic, yes. 2, continuous p orbitals, yes. 3, planar, yes, because we're assuming things that appear planar are. 4, our Hugel number of pi electrons. So we know that these are definitely pi electrons. We definitely have 6. But the weird thing is this lone pair over here. We have to decide whether or not this is in our pi system. So we need to know specifically what orbital that lone pair is in. If it is in a p orbital that's lined up with everything else, we would include it in our count for our number of pi electrons. But we know that this thing is sp2 hybridized, and it is already using its p orbital for that bond. And so it's not going to be able to also put that electron, like this lone pair here, into a p orbital that's in the exact same space, right? That lone pair is actually kind of sticking out to the side over here. And I'm going to try to draw it like a slightly different way, but it's almost like it's jutting out the kind of north, whereas these are coming into and out of the page. It's really hard to represent on like a 2D molecule, but this is just facing the wrong way, and so she's not going to spread out or delocalize with any of the other like pi electrons there. So we still only have 6 pi electrons, which means that this is going to be aromatic. It's just a deprotonated benzene. We haven't messed with the aromaticity. Okay, so down here we have a similar thing. You can get to be pretty fast at this, of like continuous, cyclic. Yeah, cyclic's the first one. Continuous p orbitals. So does this thing have a p orbital? What's its hybridization? Well, it's a lone pair adjacent to a pi bond. This is going to have a lone pair in a p orbital, certainly. And only one of those lone pairs is going to be in a p orbital. Because we know if we see a nitrogen with a negative charge, it has 2 lone pairs. So because it's sp2 hybridized, we are definitely going to have a lone pair in the p orbital. So we have continuous p orbitals, blah, 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 blah. Then we ask, is it planar? Looks planar. So now for Hugel number. So we know that we have 2 here, and then we know we have 2 here. So we have 6 pi electrons. That is going to be our Hugel number. So it's aromatic. And again, we don't include that second lone pair because that is like perpendicular to our p orbital. It's not going to be lined up with everything else in the system. Okay, so we've done a lot of aromatic examples. Let's look at this one, because this one's kind of weird. So, is it cyclic? So we have a cycle, yes. 2, is it continuous with its p orbitals? So we have p orbitals all the way around here. And here we know by our neighbor rule again that the lone pair is in a p orbital. Is it planar? Yes, it is. And then our Hugel number of pi electrons. And this is kind of weird. So we know that it has 2, 4, 6, but then what do we do with these? Do we include them in our pi system or do we not? That's kind of the big question. And this right here is a double bond that's kind of sticking out of the ring. So those have a special name, and they're called exocyclic, because like outside the ring, exocyclic pi bond. And so I made like this little like infographic about exocyclic pi bonds. when you have an exocyclic pi bond, you have to draw a resonance structure to determine whether or not the molecule is aromatic. Because the way that this is done right now, these are kind of going outside of the ring. Like, it's not a continuous path. And so you need to see, like, can it be written in a way through resonance where it is a continuous path of the p orbitals and the delocalization of electrons. So in this case, if we do our resonance arrow, push this up, we would have a positive charge here and a negative charge up here. And we know that that's the only way our resonance arrow is really going to go, because nitrogen's more electronegative than carbon. So in this case, we only have 2, 4, 6 pi electrons. So it's aromatic in that resonance structure. And so that's going to be more like what this bonding is actually going to look like. There's going to be a really strong partial positive charge on this carbon. Yeah, one thing I noticed is I have NH2 plus on here, and I have NH down here. That does not really matter, like with the protonation state of it. It would just be like neutral here versus the positive there. So it's not a big deal. Cool. So let's contrast that with this other example over here, where again, we have things going out of the bond, or out of the circle. And so we can't really tell whether it's aromatic or not, because you have things that are not continuous, like are not continuous as part of a ring. Because again, we need this kind of ring-like thing for the hamster wheel electron delocalization. Here, if we draw our resonance structures, we need to draw resonance structures for both of these, definitely. And the only way that we could draw our arrows would be going out this way, because oxygen's more electronegative. And we see if we do this kind of resonance structure here, where we have positive charges at these carbons, then there are only 4 pi electrons, and that would be anti-aromatic. And so, because doing this strong dipole would make it anti-aromatic, it doesn't do that, and it really just leans into not being like a continuous p orbital track, where, like, again, you would have to exit the ring in order to engage with this. And so it stays in this non-aromatic state because that's preferable to being anti-aromatic. This is kind of a really like tough idea to really wrap your head around. And you might notice that I'm having a hard time to kind of verbalize it too. And it's just because, one, it doesn't appear super often, and two, it's difficult to kind of justify on your own. Like the way I've just kind of phrased it is, you are always, when you do resonance structures for an exocyclic pi bond, going to have a choice between 2 of these, either aromatic or non-aromatic and anti-aromatic. If the choice is non-aromatic versus anti-aromatic, it's going to choose to be non-aromatic. If the choice is between aromatic and non-aromatic, it's going to choose to be aromatic. So which one that we favor when we're doing our aromaticity check or evaluation depends on kind of our choice of what the options are with the different resonance structures. Cool. Okay, that was a big digression. But when we drew the resonance structure of this, here we had 6 pi electrons, so it's aromatic. Okay, last one here. So this sulfur has a lone pair on it. It has 2 lone pairs, and it's a lone pair next to a double bond, so that's in a p orbital. So 1, cyclic. 2, continuous p orbitals. Yes, because we have p orbitals on all of them. 3, planar, appears to be. 4, our number of pi electrons. We have 2, 4, 6. 6 pi electrons, aromatic again. So that has been kind of a brief introduction to aromaticity, and good luck. Let me know if you have questions. Goodbye.